In this video, we'll discuss how to remove single point of failure while architecting your AWS environment. So, production systems typically come with defined or implicit objectives in terms of uptime. A system is highly available when it can withstand the failure of an individual or multiple components. For example, hard disks, servers, network links, etc. You can think about ways to automate recovery and reduce disruption at every layer of your architecture. This section discusses high availability design patterns. For more detail with the subject, how to build fault tolerant applications. So single point of failure can be removed by introducing redundancy, which is having multiple resources for the same task. Redundancy can be implemented in either standby or active mode. In standby redundancy, when a resource fails, functionality is recovered on a secondary resource using a process called failover. The failover will typically require some time before it completes, and during that period, the resource remains unavailable. The secondary resource can either be launched automatically only when needed to reduce cost, or it can be already running idle to accelerate failover and minimize disruption. Standby redundancy is often used for stateful components such as relational databases. In active redundancy, requests are distributed to multiple redundant compute resources, and when one of them fails, the rest can simply absorb a large share of the workload. Compared to standby redundancy, it can achieve better utilization and affect a smaller population when there is a failure. Now, how we are going to detect the failure? So, you should aim to build as much automation as possible in both detecting and reacting to failure. You can use services like ELB and Amazon Route 53 to configure health checks and mask failure by routing traffic to healthy endpoints. In addition, auto-scaling can be configured to automatically replace unhealthy nodes. You can also replace unhealthy nodes using the Amazon EC2 auto recovery feature or services such as AWS OpsWorks and AWS Elastic Beanstalk. It won't be possible to predict every possible failure scenario on day one. However, make sure you collect enough logs and metrics to understand normal system behavior. After you understand that, you will be able to set up alarms for manual intervention or automated response. So, what are the things we have to keep in mind while designing good health checks? So, configuring the right health checks for your application will determine your ability to respond correctly and promptly to a variety of failure scenarios. Specifying the wrong health check can actually reduce your application's availability. In a typical three-tier application, you configure health checks on the Elastic Load Balancing service. Design your health checks with the objective of reliably assessing the health of the backend nodes. A simple TCP health check would not detect the scenario where the instance itself is healthy but the web server process has crashed. Instead, you should assess whether the web server can return a HTTP 200 response for some simple request. At this layer, it might not be a good idea to configure what is called a deep health check, which is a test that depends on other layers of your applications to be successful. This could result in false positives. For example, if your health check also assesses whether the instance can connect to a backend database, you risk making all your web servers as unhealthy that database node becomes shortly unavailable. A layered approach is often the best. A deep health check might be appropriate to implement at the Amazon Route 53 level. By running a more holistic check that determines if that environment is able to actually provide the required functionality, you can configure Amazon Route 53 to fail over to a static version of your website until your database is up and running again. So these are the things we have to keep in mind while creating a redundant infrastructure and to counter the detect failure. Now the next topic we need to move on to is durable data storage. So your application and your users will create and maintain a variety of data. It is crucial that your architecture protects both data availability and integrity. Data replication is a technique that introduces redundant copies of data. It can help horizontally scale read capacity, but it also increases data durability and availability. Replication can take place in few different modes. One of these is synchronous replications. So synchronous replication only acknowledges a transaction after it has been durably stored in both the primary location and its replicas. It is ideal for protecting the integrity of data from the event of a failure of the primary node. Synchronous replication can also scale read capacity for queries that require the most up-to-date data. That is called strong consistency. The drawback of synchronous replication is that the primary node is coupled to the replicas. A transaction can't be acknowledged before all replicas have performed the write. This can compromise performance and availability, especially in topologies that run across unreliable or high latency network connections. For the same reason, it is not recommended to maintain many synchronous replicas. One thing I would also like to highlight here is durability is not a replacement for backups. Regardless of the durability of your solution, this is no replacement for backup. Synchronous replications will redundantly store all updates to your data, even those that are results of software bugs or human error. However, particularly for objects stored in Amazon S3, you can use versioning to preserve, retrieve, and restore any of these versions. With versioning, you can recover from both unintended user actions and application failures.